we started talking about the source of electric potential. And that source of electric potential is called a power supply. So when I look at this power supply, a lot of times people will say that it's a voltage source. That is only partly true. It's more complicated. And I've said this in lab, and I'll say it again here in a little bit. So our source of electrical potential is a power supply, and the best example of a power supply is a Van der Graaf. So in a Van der Graaf, that the only way you can have a continuous current, that is a continuous discharge from the Van der Graaf to the discharging sphere, is that the current carried by the belt must equal the current discharged into the air to the discharge rod. In other words, if you want continuous discharge or current, the current outgoing must be the current ingoing. This is true for a power supply or a battery. So for a battery and a power supply to work properly, the current coming out of the battery must equal the current going into the battery. If that is not the case, then you do not have a working power supply that's going to give you what you want. So the model that we've been dealing with has been these two conducting plates, but something is missing. And this is what is called the EMF. This EMF stands for electromotive force, which is one of the most hideous names that you could have given this thing. And we'll talk about what it means here, and I'll write it out here in a minute. But let's look at the Van der Graaf. So if you look at a Van der Graaf, so note, I have a positively charged Van der Graaf. So that means that the lower green plate is negative. The upper positive roller in yellow, and what it's moving here is positive charges, not electrons. So when we look at the Van der Graaf, what we see here is it moves charge from the negative plate to the positive, from the negative roller to the positive roller. So what moves them? It's the force of the belt. Okay, no surprise. So, but the belt is not electrical work. So this is non-electrical work. And the way the belt moves is the motor. So the motor moves the charge up to the Van der Graaf shell. Now, here's what we're saying. If I have two positive plates, it can't be electrical work that moves the charge from the negative plate to the positive. Why? The negative plate is attracting the positive charge. The positive plate, is repelling the positive plate, the positive charge. So it has to be non-electrical work that is moving the charge up the incline. And this is this missing piece. What does the work? In a battery, it's called an EMF. And that's what you see my question is. What moves the charge up the incline? So what I'm going to do here is that I'm going to really pay attention to these two plates. Now, to conserve space, instead of drawing them vertical, I'm going to draw them horizontal. And they go something like this here. So then I'm now going to change colors. Now, why am I changing colors? Because we typically assume that the red terminal of a battery and the black terminal, I messed up. My apologies. The red terminal is positive, and the black is negative. And since that's what we typically associate with batteries, I'm going to stick to that. So here I go. What happens? So in your mind, you need to think of the Van de Graaff to explain this incline work. Okay, here we go. So here's my Van de Graaff picture now. So the first thing I'm going to do is that I'm going to start with uncharged plates. So I start with uncharged plates. And then what we find here is that the belt transports electrons. From the red to the black. So picture-wise, what do I see here? I have a plate. Now remember, this is really a roller, but this guy is my positive, right? This is my positive plate. The question is, why does it become positive? And then here's my black terminal. So I shouldn't have drawn the positives yet. So here's what I'm seeing here. So what I'm seeing here is that I have two belts right here. I'm sorry, I said belts. These are the rollers, like the Van de Graaff. Now, on this roller is a belt. And what we know here is that the belt goes in this direction like that. So what am I doing here? I remove electrons from the positive plate. Now note, if I remove electrons from the positive plate, that means if I have a neutral uncharged plate and I remove electrons, it means that it becomes positively charged. And so these electrons are being removed, and as they're being removed, we're moving them in this direction. So what actually happens here? So then again, this guy right here is the belt, just like the Van de Graaff. So what we're seeing here is that we're seeing this here, that there's the force of the belt, but the force of the belt is the same as the force of the motor. But from now on, I'm not going to call it the motor. I'm going to call it the force of the non-electrical work, where F and E, where NE stands for non-electrical. So it's a non-electrical force that's actually doing this. So that means we are applying a force in this direction to move the charges. I start with uncharged plates. I take electrons off of the red plate. It becomes positively charged. And if I bring it over to here, it now starts to acquire a negative charge. Now, here we go. So if I continue here, so what you're finding here is that both the positive and negative plates apply an electrical force on the charges. And if I redraw this, what I'm really doing is that I'm really looking at this type of thing here. So if I come down to here, and what I'm going to do here is that I'm going to focus on just one of the charges here. So here I go. So what I'm going to do here, so I want a clean slate here. So now let's go look at that. So I'm going to focus on one of the charges. So if I focus on one charge, here's what you're going to see here. There's a force produced by the non-electrical force, right? So there's a force going in this direction. Now, when you look at the plates, there's two forces here, right? There's the force of the positive plate, and there's a force of the negative plate. So I'm going to say here is that what you're seeing here is that, once again, look what my language is. The force of the motor is the non-electrical, whereas the force of the plates is going to be negative E of the electric field between the plates. So I have two competing forces. So at the moment, what you're seeing here is that in this situation, we see that the non-electrical force is greater than the force of the plate. And why is that? Because charge is accelerating towards the negative plate. Why? There's a net force acting on them. Okay, there's a net force acting on them. So if that's the case here, so now what we want to do is that what happens here? At some point, what we're going to see here is that, I probably should have paid more attention to drawing. I don't know what just happened. At some point, I should have drawn not so many charges, but here's what we're going to find here. And this is the third point. This is eventually enough charges will build up on the plates to reach equilibrium. And remember, the word equilibrium means that the net force is equal to 0. So what this means, so physically, the motor cannot, I don't want to say pump, it cannot pull out any more charge at this rate. And therefore, it reaches equilibrium. So what I'm really saying is that I'm looking at my picture now. So if I look at my picture, what happens here is that now, when I look at the force of the plates, these two forces balance each other out. So what this means here is this: equilibrium implies that the net force is equal to 0, which really means that the force of the belt is equal to the force of the plates. When this is the case here, then that means here is that the rate, how do I say this? So now what this really means is that now charges move at constant velocity. So here we go. Remember what I said here. The most important thing about a battery here is that the current going out of the battery must equal the current going into the battery. So what you're seeing here is that the only way that we can have this, so the only way to maintain this is if current going out equals current going in, right? That's the only way. So that means here is that I mean this, that the current of the belt must be the same as the current that's outgoing, and that must be the same current as it's incoming. Right? That's what we mean. That's what we mean like that. So this means here is that now here's the key point. The function of a battery, remember, I could call it a power supply, is to produce and maintain this charge separation. Because if it maintains this charge separation, then I now have the current coming in versus the current coming out. So you could imagine here is that if we now start to really think about the details of this thing, how would I say this here? So I would probably come in and look at this guy here. And it looks like this. So, okay, so the amount of charge separation is solely determined by the strength of the motor. Okay? So remember, when I say charge separation, I mean this thing right here, right? This is the only way you can maintain charge separation is there. So we can compare things here now. So if we're talking about, so as an example here, we can talk about real batteries. So if I think about a car battery versus, let's say, a double or triple A battery, something must cause charge separation. So when you're looking at this, we say that this is a 12.6 volt battery, and this is a 1.5 volt battery. So the question is, what is the strength of the battery? So the strength of these batteries is that these batteries are a chemical reaction. It's a chemical reaction. So in essence, this is their motor, right? It's their motor. That's what moves the charge here. So here's what we know. And what we know here is that I'm going to look at the language now, because the language is something that we got to be really clear about that. We know that E is equal to the voltage here. And I'm only going to look at the magnitude of this guy. So what this tells me here is that we can see that the voltage is this guy right here. Now, when I look at my situation, what is it that I'm talking about? Well, if you're looking at this thing here, here's what you're finding here. Note there is an E field inside the plates. And what you're seeing here is that this E field looks like this. It goes in this direction, and this is the E field inside. By the way, it's different than the field outside. And so what we're really looking at here is that now I'm going to change this, and here's what we want to be careful about. So this guy here is the current that's going out. So this is the outgoing current, and this is the direction of the outgoing current. Right? So that's my outgoing current right there. But there's a second current. And the second current is doing what? It's also coming into the battery. And this will be the current that's incoming into the battery. So as long as I have charge separation that's kept constant, then that's a condition here. So now we know that there's a field that's moving the electrons. And so what we're seeing here is that, so we then say that inside the battery, okay, so now inside the battery is the voltage of the battery. And so when we're talking about the voltage, we're talking about from here to here, there is a voltage inside. Okay, there is a voltage inside. There is a high and there is a low. So when I look at the voltage of the battery, the charge has to fight against what? It has to fight the electric field due to the plates times the distance that it travels. Now, if I replace the E field with E times F, that would be the electrical force. Maybe I should be a little bit more careful. So then the E field of the plates should be the charge of the carrier. Ah, man, I'm messing up. So the force, the non-electrical force, has to balance out the field of the plates, right? And that's what we said up here. In order to maintain this function, these two forces must be the same. And so now I'm just writing that out. And so when you look at this thing, here's how they write it. They write this as F NE times D divided by E. So all I did was replace the electric field with this. And here's the language. This is what they call the EMF. The EMF. EMF is defined as the electromotive force. And what I'm saying is that this name is what? Is hideous. Why do I say this name is hideous? Look at the thing. Is this expression force? No, it's not a force. It's a voltage. It's a potential. Okay, it's a potential. So it's not even a force. It's like, ooh, nobody ever says electromotive force. They call it the EMF, and that's what I expect you to do. So what does this mean here? The EMF is the potential of the non-electrical field slash work in the battery. And if we're talking about car batteries or AAA batteries, what this really tells us here is that this guy is the chemical potential. We use the transfer of electrons in order to keep charge separation. So now what I want to do here is that I want to go in and I want to start looking at the physics so that you have some visualization. Okay, here we go. So now what we're going to have here is that I want to physically interpret the role of a battery. Remember, the proper way to say it is to say power supply, not battery. Because a lot of people think that it's a voltage source. It is not a voltage source. It's more than that. So here we go. So now let's set up let's say that we have a AAA battery. So what's a good model for a battery here? So I'm going to go, let's say that here's my battery. And the way the battery works here is that it has a positive terminal right here. And I'm going to color this guy in red because we know we have the flow of positive charge. So what I know here is that there's a potential across this battery. So what does that mean? That means there is a high potential. There is a low potential here. And so what happens here is that think about what we have. We have a belt. But now what I'm going to do is that I'm going to assume that we don't have a belt, we have an escalator. Because this does not convey, rightly what we should be thinking about it. So here we go. So now I have a wire, and it's going to be a thick wire. And then it goes, there's an incline. And then I have my device, my load, as we say. And then the wire comes back down. And then what it does here is it reattaches back here. Okay. So now what do I have? I have charges. So now I gotta be careful. I have charges everywhere, right? Everywhere in the wires in my device, I have charges everywhere. Now remember, these are positive charges now, because that is the flow of conventional charge. So what happens to these charges? So let's go through that. Let's go through the steps here. So the first thing that we see is that charges lose electrical potential energy as they move from high to low electrical potential energy, right? They're moving, so they lose potential energy. And in the language of the resistors, they lose it to heat. So now let's look at the language here. This is the current that's outgoing. So these charges are moving. They all move simultaneously. They're going like this. And then now I have charge flowing into the system, into the battery now. So what I'm going to imagine here is that I have an escalator. And so when I look at this guy, I'm seeing something like this here, and it goes, so this guy right here is my escalator. And what do escalators do? They move up, right? So this is my little escalator that's moving charge from where? It takes a charge and it starts off at low potential energy, and that now it starts moving it. So when I look at my charges are in a flow in a way that they're all moving in the upward direction. So here we go. So the second thing here is that the battery provides a chemical potential, right? It provides a chemical potential, which is what we call an EMF. It provides a chemical potential that does work. So what do I mean by work? So what we mean by work here is that re-energizes the low potential charges to high potential. In fact, that's so important that I think I'm going to color that guy, right? That is so important. So what you're seeing here is the sole goal of the battery is to re-energize the charge. So here's what we then say here. Because we raised them, we then say that the voltage of the chemical potential is the same as the EMF. And in steady state, that becomes the voltage of the battery. So here we go. So then the third thing here that we should be saying here is that I need to keep charge separation, right? So to keep constant charge separation between the positive and negative terminals, we then know that the outgoing current must equal the incoming current. That is required. So that means then when I look at the incoming current, this right here is now the incoming current, right? That is the incoming current, just like the Van der Graaf. So what I have here is that I have a system set up here. Now I'm going to show you a little bit of a white lie, but I'm going to wire this guy up so that you can see me do that. So this is a link on the applet, on the lecture page. And this is called the FET circuit thing. So here I go. So what I'm going to do here is that I'm going to look at a light bulb. I could put a resistor here, but a light bulb's a little bit nicer to see here. And then here's my circuit. So if I now put this all together, look what I'm going to see here. So what you're seeing here is that you're seeing what? You're seeing, let me grab a picture of this thing. Oh, sorry. So you could see what's coming out of the battery is what's also coming into the battery, right? And that's the way this thing has to operate. So this means that I have a constant EMF inside. It's raising it up. So if I now come in and I go back to my notes, here's the thing that you want to be paying attention. So this applet here is the FET circuit kit. And so here's what I was talking about. You're seeing that this is the outgoing. And this guy right here is the incoming. And what's super important here is that, so if I come over here and I add just one more piece, just to be clear, if I outgoing does not match the current coming in, one draws too much current from the battery. And what you find here is that then the battery stops behaving, as we would say, linearly. So you need it. So we don't have a proper battery if you're pulling too much current. By the way, just to re-stress this whole thing here, I want to give you one more analogy, because I think it's a very good one here. And the analogy that I want to look at here is what happens in a water fountain. Okay, what happens in a water fountain? So here's what we know about a water fountain. We have a pump, right? We have a pump. So let's say that we have a pump here, and we know that the pump does what? It's then going to move water. So what do we mean when we say water here, right? So this is my water pump. Well, we know that a water pump may have water that's falling down. Let's say it's falling down some incline, or it doesn't have to be an incline. So now what happens to the water? What we know here is that the whole goal of the pump, everybody says, is to make sure that we have constant water flow, right? But we got to put it into the right language. This is high gravitational potential energy. This is low gravitational potential energy. So what you're seeing here, as the water goes and it slides down your water fountain, what you're seeing here, down here at the bottom, is that you have low gravitational potential water. So what does the water do here? So the role of the water pump is to re-energize the low gravitational potential water to a high gravitational potential water. And when you do this, then you can have continuous flow of water. In other words, the outgoing current must be the same as the incoming current. If you can't maintain this, you're not going to be able to have this. That's what a battery is. Okay? So people always have a tendency to say, oh, I have a dead battery. And one of the biggest misconceptions is that you could take your digital meter and you could measure the voltage across the battery and just say, hey, oh, this is a good battery, or this is a bad battery. You can't do that. A battery is more than a voltage source. A battery is a power supply. It demands two things. You have to set up a height, that's the charge separation, and it has to maintain the outgoing current with the incoming current. It has to do both, not one.